Okay, yeah, some of this presentation will be about me hugging a robot, but most of it is going to be about a bubble gripper that we've released the design files and build instructions for online. Something we are still doing research on, but we got asked a lot for bubble grippers, so we put the designs online so that people could build them themselves. I also want to take the opportunity to ask you to grab a handful of stickers over there on the front table. You can bring them back to your lab mates. You can drop them on other people's tables. Power Robotics, you can put them on your own table. Feel free. I have a ton and I'd love to not bring them home. Okay. So a brief introduction of myself. I studied mechanical engineering at Drexel and got the opportunity while there to spend some time in KAIST in Korea. I started on humanoids working with Mini Hubo, which I'll show a picture of, and Hubo. At KAIST, I was sent there to learn how it was built, learn some aspects of the manufacturing process, and document that for use back in America. I really enjoyed Korea, so I went back, finished school, went back to Korea, and spent 2.5 years at SimLab. If you know the Allegro hand, which is a hand used frequently in manipulation research, I built, sold, and supported the first 20 while I was there. I then moved to Disney Research. Katsu found me, and Jihyung found me. I was very happy to move out to Pittsburgh and work with those two. And that's where I got into soft robotics, started building tiny humanoids with bubbly sensors. And ultimately that led me to Toyota Research. I still build robots with bubbly sensors, and I'll show some of that soon. Just for fun, here's a picture of me back in school. I think I look exactly the same. And that's Mini Hubo, which I'm not sure if it was technically open source, but it is a cousin of Darwin OP. This was designed by Romola, Dr. Dennis Hong's lab. And then our lab at Drexel was one of the labs that was tasked with building it and offering kind of process improvements and just updating CAD and just kind of helping along the process of making sure the documentation was good. But that was my first little humanoid. A lot of hard edges. I had no idea about soft robotics at the time. Okay, so what I'm here to tell you about today is a website that we built with design files, build instructions, a bill of materials for our soft bubble gripper. It's available under a Creative Commons license, and this link is simple, punyo.tech. So if you don't grab your phone quickly enough, that's fine, but it's also on a business card over there. But I'll walk you through the documentation and show you what you can find there if you're interested in a bubbly gripper for manipulating. So a little bit of an overview about what this gripper does. It's passively compliant. It's basically an air-filled latex balloon. You can make it out of silicone and other stuff too, but latex is super durable. You can see that alone, without even talking about the sensing, it's pretty capable as a gripper. It's grippy. It wraps around objects. It doesn't have a lot of articulation. It's pretty simple construction. It's fairly durable as well. Inside of it, inspired by the likes of gel sights and finger vision and all the various visual tactile stuff out there, it has a depth camera inside. You also put a normal RGB camera inside, but in the first version and the version that's available online, it's a PicoFlex. So by putting a PicoFlex inside, you immediately get a point cloud out of the thing. So you can do geometry sensing of whatever you're smushing into it. With the geometry, you could do things like pose estimation of objects. You can do recognition of those objects. You can also use a mono image that comes out of it also. That's the IR stream. And you can, basically, it allows computer vision people to be tactile sensing people. You just run the same object classification training, and now you can do tactile image-based object classification, stuff like that. So visual tactile is very powerful, whether you're using the depth sensing or not. Another feature this thing has is a removable bubble. So they're all their own little modules. You can swap them out when they're worn out or if they pop. You can swap them out with something that's made of thicker latex or a different material if you're allergic to latex. You could even put different patterns on the inside, and I'll show you what those patterns are for. But being able to swap these out very easily allows you to kind of keep all the electronics in one place and just rip these things off, replace them when you need to. That is the hardest thing to know how to build, honestly. I could tell you nothing and you'd be able to figure out the rest. But this part is where the documentation really comes into play. And just because when I say bubbles, people say that can't possibly manipulate anything without popping. They are pretty durable. We've done thousands of grasps. We do on hardware. The object classifier was trained on hardware, just grabbing stuff in the sink. Once in a while, you'll hit a pointy edge and you can patch it just like Baymax. You can use bike patches, you can use a little piece of latex and some rubber cement, but it's more durable and usable than it looks. And I'm not biased, I promise. So those dot patterns, just like finger vision or any of the other visual tactile sensors, being able to track dots can give you a sense of depth, but you also can use them for shear. And we can do shear tracking. We can do minimal slip understanding. It's similar to the other visual tactile sensors. We're only sensing at about 40 hertz maximum. So you're not going to prevent slip necessarily unless it's a nice low slip. But knowing that it happened is pretty useful. So you can use lower density dot patterns and you can see, you can get a better depth image, or you can use higher density dot patterns and get a worse depth image, but better shear sensing. So this is another reason why that hot swappability is important. Frequently, we'll use a pure white bubble on one side and a high density dot pattern on the other side and kind of get the best of both worlds. So why did we document this in the first place? So within TRI, Toyota Research Institute, within Toyota, and within some of our partner Toyota family companies like Wolf and Alpha over there, we were getting a lot of interest. They wanted bubble grippers. We also have university partners that TRI funds, and they wanted bubble grippers. Now, I spent months building bubble grippers, and I didn't intend to be hired to be a bubble gripper manufacturer. So basically, I decided at some point after about 5 bubble grippers that we're going to redirect, we're going to document and allow other people to build them too. Mad props in the middle. That is a really cool group within TRI that it stands for machining and design, prototyping, and robotics operations. And they will build these things now that they know how in mass. They mass produce them, and that's for internal purposes. And a few of these universities have built their own since we released the documentation. So I'm no stranger to understanding the tech transferability and the purpose of good documentation in that. I got inspired. There's a lot of documentation I don't like doing as an engineer. It's hard to get me to document my work, but when I'm allowed to build a website around it, you got me. My parents are graphic designers, so presenting data in a useful way that basically enables people to build robots, I think it's the perfect mixture of what I love. When I was at Drexel and got sent to KAIST to document Hubo, we built this website. Now, this was internal to the 7 universities in America that got Hubos, but it was thorough, and I loved doing it. It took a lot of time, but I learned kind of how to keep things simple, how to present a lot of data in a concise way. And ultimately, this is where my mind went when it was time to document this bubble gripper. Also, I was an intern at the time, so that kind of tedious work is perfect for interns. At TRI, I convinced HR to let me set up a cooperative education program. So that is 6-month stints for undergraduate interns. We take master's level now too, but it was really important to me to get the undergrads in. have a more diverse hiring pipeline, give them the opportunity to come to Boston and work at a really cool place. And when I got the okay, I went straight to my alma mater, Drexel University. I knew how their program worked. I knew that they had strong students, and I knew that they had minimal robotics programs. So I thought it would be a really good opportunity for getting people involved. This picture is Siha Junhai. She actually wrote all of the documentation for this bubble gripper. She spent most of her time over 6 months. It wasn't her only job. She had some other cool, fun stuff to do. But she did an incredible job of learning how to build bubbles better than me, teaching other people how to build them, writing all this documentation, making videos of every step of the process, and working with individuals who had never built bubble grippers before to kind of test out the documentation. If they could build it without asking her any questions, she was done. And she learned a lot about technical writing, how to keep things concise, how to organize, attention to detail. A lot of things are missed when you're a young student just trying to get the job done. But this was she did an incredible job. And if you go to the website, you'll see that. So a quick tour of what we've released. So if you go to the website, punyo.tech, you'll be met with this page on the left. This is basically just telling you a little bit about the project. There's some history of the project down at the bottom. You read the license, you click OK, and then you get access to all the files available. There is a long PDF. I think it's 94 pages of how to build this thing, but we give you every single step. We tell you which glue to buy and where to put it. I wanted to leave nothing out, and we barely get any questions. So I think we did a crazy extensive job of this, but take a look. We got a bill of materials, of extremely pretty bill of materials, and a zip folder that has a bunch of files in it. And those files include the documentation, a spreadsheet that we use for tracking all the bubbles we build. So when you go look at a serial number that you wrote in the back, you know what the thickness of the material is, the dot pattern you used, the colors. There's vector files for laser cutting, the stencils for the dot patterns. There's vector files for cutting the acrylic pieces that are involved. There are STLs for the 3D printable files, and there's also the SolidWorks files so that you can play with the bubble gripper design on your own, change things, apply it to your own robot. Like I said, there's also videos of every step of the way, and this is, you could probably get away without reading the documentation, although I should not have said that. But on the right, you also have the history, which is basically just all the papers that we've published that are relevant to this work, and some papers of partners even that have built bubble grippers and used them for some cool research. Also open sourced is the contact simulation that we use internally when prototyping control schemes with the bubble grippers. So this is called the hydroelastic simulation. There's a lot of documentation about it. If you have heard of Drake, that is a robotics control and simulation framework that TRI is actively developing. It was originally just MIT, but TRI has taken over the development. And since then, the Dynamics engine has had a lot of work done to it as far as interesting contact simulation goes. So moving beyond just point contact, we have some soft stuff in the works, but this has been released. And as you can see, instead of point contact, you're getting contact patches and you're getting pressure maps. And that is really how Baymax rolls. You know, the whole reason you make them soft and bubbly and compliant is so that you can make patch contacts. And if your simulation isn't doing anything like that, you might as well not be using it. And then just a quick slide on how we're pushing this bubble gripper. So Mass Robotics is a cool, big event in Boston that happens every year. It actually lasts a couple of days, where robotics companies, a lot of them are in Boston. I think plenty come from elsewhere as well. But you set up booths, and really the target audience is children and young adults, students in the area. And we set up, they can come poke our bubbles. We have all this, all the tactile information streaming, so they can, you know, pick something out of their pocket, stick it into the sensor and see what the point cloud looks like. They can ask questions. I've had a couple 10th graders drop off their resumes. I think that's really cool. And then we're also starting to go to conferences and set up tables just to kind of see where the interest level is and maybe adapt the bubble gripper to meet some of the needs that researchers have. And then just a couple examples of kind of the fruits of it being able to be built by other people. Something I would have never thought of, turning the bubbles around, and instead of a bubble gripper, it's a nudger. And they can build maps of the world, pushing things out of the way. And ultimately, you can imagine having a gripper on the other side or something that goes and grabs the thing that's made available by pushing this clutter out of the way. And then our partners at MIT have tried to model the compliance in a series elastic way. So a six direction series elastic model of this thing allows them to understand the forces that they're applying on a tool using this bubble gripper. So just some stuff that would not have happened if these students couldn't build their own bubble grippers and have a nice compliant visuotactile sensor on their gripper. So all that stuff I showed previously, that's what's available now online. We have updated it to accommodate a RealSense as well, because if you know anything about the original PicoFlexes, they aren't available anymore. So unless you have some stashed away, if you want to build this thing, right now we're in kind of a weird zone where you can't unless you, I don't know, buy them on eBay or something. But the RealSense works really well. We had been thinking about incorporating it, and we're finally forced to. The depth results actually are even better than before, so that's good. There's a new pattern that makes it work better. This works better with the RealSense. It's a pattern that they suggest as like the perfect pattern. When you have control over the pattern of your environment, this is what you should use. And then we're also building kits. So if the only thing holding you up is you don't have a laser cutter or something like that, you can talk to us and tell us you have a great idea for how to use this, and we might provide a kit. So we have kind of a pilot program going right now where we have 10 universities and industry partners that have said, it would really be cool to have one of these. This is what we do, and we're going to be shipping these out quite soon. We're lending them out. All the design files for that RealSense version, the new instructions for the modifications to it, including some process improvements, are coming soon. They'll be online at some point in the near future, probably next month or so, as well as a ROS package. So previously, we were running it through Drake. We would tell you, download this ROS package and use this thing. And it's pretty easy to cobble the software together. It's a fairly simple setup. But now we've cobbled it together, and there will be a ROS package, so even easier than before. Okay, so this is a slightly separate part of the talk that just shows where we went with it after doing that. This is very Baymax related, so I didn't want to miss the opportunity to share. So you can see here that basically I broke the fingers off of the bubble gripper, and now they are paws on a bimanual manipulator. So the whole theory behind the bubbles in the first place was we put them on a gripper so that we could get them tested internally. All of our other TRI groups doing manipulation are doing end effector kind of stuff. So we wanted to put it on end effector so that other teams could use it. Since coming from Disney, I was pretty dead set on whole body manipulation and really wanting to squeeze and hug things. So as soon as I could, like I said, I broke the fingers off and made paws out of them. And now we're doing whole body manipulation at TRI. So taking that compliance and sensing and putting it all over the body. So the robot we have at TRI, it's a prototype based on Jayco arms underneath. So we got our hard robot underneath, so we know how to control it. And it's position controlled. So we put these bubbles all over it so that we can have some understanding of torque and force going on. So what you see, those gray airbags, or those gray bubbles. They are airbags that are basically just imagine the pool floaties you put on little kids in the pool. Put them on your robot arm, cover them with something protective, hook them up to a pressure sensor, and that's all that is. And that gives us the ability to treat this like like a robot that understands torque. So we can stop when we hit something. We can treat it like a cobot and kind of squeeze things and move it around. But you'll see up at the top left that that's the readings that the sensors are outputting. They don't know if you poke them on the inside or outside in this one. There's a next version that they might, but it's simple, and the control algorithm is simple. It just goes and grasps until it hits a threshold, and that's how we grasp a lot of objects. Another set of sensors this has is there's an array of sensors that we call inductive sensors. They're based on inductive coupling of a board and a metal plate, and we can put whatever we want in between. There's foam, or you can put a little airbag. You can put a stack of fabric. It doesn't really matter as long as it's not more metal. And when you array these, you get basically the orientation of the plate. You get the pose of the plate. So if you squish it inward on the foam, you understand that a force is being applied, and then you also get the orientation. So again, we're getting sort of in an array, we're getting a sense of the geometry of the objects pushing into our chest, but it's a really, really coarse geometry. So here's some videos of it in action. We don't just do whole body grasping, we do these paw grasps as well. You can see that the friction is playing a big role. It's pretty easy to, because of the softness, pretty easy to kind of just apply this to different objects around the house and just squeeze up. We didn't design the controller for these boxes specifically. We designed it around a hamper, and then we just grabbed a bunch of stuff around the lab and made it grasp it. Here's the hamper. This was the major test case. So the idea here, the reason we're targeting these big objects, again, like I said, almost all the manipulation groups they're trying to do dexterous stuff. They're grabbing tools, they're cutting things, they're doing in-hand manipulation. It's all gripper stuff. There's this whole class of objects in the house that is being ignored, and these are the big objects, the heavy hampers, the trash cans. And we actually did research with older adults in both Japan and America, and they said if a robot could do one thing, it would just be the heavy stuff. It's like what you call your grandchild over to help with. Bring the kitty litter in, or the big, Amazon heavy box. So that's why we shifted and felt confident in shifting over to this. We still have a bunch of groups, so we have diversity of manipulation strategies happening, and we wanted to focus on these big objects. So you'll see we got the trash cans, and this is the same simple grasp controller working on all these things. It's like the simplest possible thing you can imagine, but it's made capable by having the compliance here. We don't need perfect positions. We don't need to get under the little ridges on the trash can just to make it work. Things don't slip and slide. We've even added a lot more friction to the insides of these bubbles since, so that these grasps are, you can't even rip the things out of the grasp. And then just to get a sense of how compliant these bubbles are, you see it's a very strong grasp, but there's a lot of motion in there, and that's okay in a lot of cases. If you need a rigid grasp, we can use other parts of the robot, or we could put things on the back of the hands and maybe use that, but that's not our goal at the moment. It's really just grasp stability and the fact that it's not dropping anything, and it can handle these bigger objects that the grippers couldn't get around before. And then I mentioned that we can now treat it kind of like a cobot. So we use, we basically recreated something that we did at Disney, which is, what if you could just grab a bubble and put the robot where you need it to be, instead of scripting everything or having to like nudge a joint in the direction you want it to be. We don't need code if you can just position it, save a keyframe, position again, save a keyframe. So this allows some of our researchers that don't want to get into the code to kind of just script a motion or something like that and get the robots out of the way if necessary. It's really just a much more intuitive way to interact with the robot. And then I promised a robot hug. It actually feels amazing to hug this robot. Again, I am not biased. We have hugged other people at TRI. We've hugged visitors, and they at least all tell me they like it. This was just that's again, the same grasp as the hamper. but with the thresholds turned down just a little bit. So the idea was we had one researcher that just he basically he couldn't not do it. And he sent us a video on Slack of this robot hugging him at his house because we were all working from home when most of this development was done. And once we brought everybody and the robots back into the lab, we all had to try it. And we actually have it's gained some traction in the sense that, you know, our CEO has tried it, Gil Pratt. Some of our PR team has tried it, and they keep talking about, you know, how they want to do more with it. And it was not a concept of ours. We were not out to build a hugging robot, but just trying out that hamper grasp on people has really kind of directed the project into a much more we're not focused on HRI, but we know it's going to be a big part of this robot. So we want this robot to touch things. We want it to bump into things. We want it to use its whole body to get physical tasks done. But another goal of TRI is it's home robotics. So do you ask the older adults and kids to get out of the room when you do the dishes? You can't do that. So we've basically, I think, just gotten to the point of being around humans and being comfortable doing it a little sooner than we expected, just based on this fun little experiment. But we're kind of doubling down, and touching humans is going to be a major part of the next few years. So back to bubble grippers. If you are interested in bubble grippers at all, you can go to punyo.tech and just poke around. If you're interested in getting more information or potentially a kit, you can snap that QR code, or it's on a business card up there, or just go to punyo.tech/survey. And if you just want to ask questions, or, you know, whatever, Alex@tri.global is me, and punyo-info@tri.global is me. I'll answer your questions, but I also have a couple other people answering questions there too. So that is it. Thank you.
I think we can take a couple of questions.
Yes.
Is it currently air in the bubbles, and you can dynamically change the pressure?
Yeah, you can. So it's air. It's like 1.5 psi, I think, with the thickness of latex we mainly use. We just pump it up with a bike pump and let the air out at the end of the day. They don't leak very much at all. We've left them inflated for weeks with no noticeable change. One other thing that intern Siha did while she was with us was she built an inflation and deflation rig for it that was computer controlled. And we did some stiffness, variable stiffness tests where you'd you'd stiffen up to mashed potatoes or something like that. But you can't really you can change the stiffness by thickening the material, and then you can pump it up to like the same height. And now you haven't changed the geometry, but you have changed the stiffness. But if you're just deflating and inflating, you're changing the geometry while changing the stiffness. So there's this interplay. So she wrote a paper. She actually led a paper as an undergrad at TRI, and you can see that in the history section, on this geometry variability too. So if you're going to go grab a plate or something, you flatten out your hand. And with the bubble, you can't really do that. You just kind of bash the plate against the side of the sink. So what she did was she deflated the bubble, she could get underneath, and then you can reinflate the bubbles and do stuff like that. So this variable geometry and stiffness interplay is a very interesting thing to play with. Yes.
What about the accuracy of this bubble system? Because from my understanding, it's not software, that could be enough for different imaging, for example, for the what is the accuracy to have another take?
The accuracy of like force sensing, or
Correct.
So we are actually only currently starting to care about real forces. Like we could pump these up to what felt good. You know, it's like I think they're ready, and we don't even calibrate. We just kind of run it and it works. Yeah, thanks to compliance, it doesn't, and thanks to hampers not complaining about how hard you squeeze them. But recently we're starting to dive into motion planning and contact aware, basically force-based, rich contact. We know where we're making contact. We're starting to try to do moves where we actually need to know what the forces are to push something or flip something, those kinds of things. So we're in the process of calibrating and understanding repeatability, precision, stuff like that. But until now, our philosophy was kind of like, it doesn't matter, it works. So it's accurate enough. Yeah.
Thank you so much.
Thank you. Stickers, don't forget.